seems like a beautiful, sunny, and warm place, but she tells me she actually came yesterday from wet and cold Germany. But let's see. Maybe we'll hear more about what that's about. And let's just start. Welcome, Jenny, and let's hear the story for gravitational lensing.
Good afternoon, and welcome to my talk. Cordial thanks to Whaley Penn for the invitation. And for the younger generation here, my talk is called Lensing of 69, in reminiscence of the summer of 69 and the famous concert at Woodstock, where people asked how much standards and traditions do we actually need, and how much can we actually explore life on our own. And in a similar way, my research is concerned about the question, what impact do models have on the interpretation of our data? So how much theoretical framework and how much model assumptions do we actually need in order to interpret our data? To give you a very down-to-earth example, let's start with some biology. So if we want to ask the question, who's behind the tree, what would you say? Come on. Just a guess. Answer the question, who's behind the tree?
Okay, cool.
Okay. I mean, most people have been to the desert, we've seen a lot of reptiles, so most people would of course say, yeah, it's a chameleon behind the tree, of course. But if you live close to Area 51 and you get abducted by aliens every night, you see one of your kidnappers behind the tree. And the funny thing here is that we cannot answer uniquely who's behind the tree based on this very sparse data that we have. So what we do here, implicitly or explicitly, we let our experience guide our perception to either infer this or that as a solution to the question who's behind the tree. But the most general answer and the most authentic and true answer we can give here is only something or someone with two green hands and a green tail, because this is the observational evidence that we have in order to answer this question. The rest is just a model assumption based on our prior knowledge. Funny enough, keep this in mind, now we're switching one scale upwards, and if we want to answer the question, what's behind a strong gravitational lens, we can employ exactly the same principle. But now we have a problem. We want to infer what's behind the strong gravitational lens, so we want to know what is the source emitting light rays towards us as observers, based on the fact that we have a strong gravitational lens along the line of sight between the light emitting source and us. And according to general relativity, the light rays do not follow straight path lines, but they get deflected by this strong gravitational lens. So as a result, we see multiple highly distorted images of the source, which is hidden behind the lens, and we have to infer the source properties based on distorted multiple images. And the other problem that we have here is that we do not see the source, but we neither have full knowledge of the lens, because the lens contains of luminous objects like stars, dust, galaxy, the baryons in the galaxy, but they also consist of what we think is dark matter, if it exists, causing these huge light deflections. So we have no direct detection of dark matter, meaning we have to infer the distribution of dark matter in the lens as well from this scenario. So what we have as sparse data and observations usually are these highly distorted images, and they have certain symmetries depending on the light deflecting mass densities, depending on the symmetry of these objects. For instance, on galaxy scale, we have these giant arcs here. If we go to galaxy group scale as gravitational lenses, the symmetry gets broken. And if we have galaxy clusters as the largest lenses in the universe, we just have like giant arcs and some little multiple image positions here, but there is no symmetry anymore. Now, how can we ask the question, what's behind the gravitational lens, and what can we learn about the gravitational lens? So we need a little bit of mathematical formalism. So let's have a look into that. So in a very two-dimensional sketchy way, we assume that we have a source in a source plane at a certain distance between us and the source here. And then we assume that this light emitted by the source travels along an empty light cone in cosmology, and it gets instantaneously deflected at the position of the gravitational lens, which is assumed to be in the lens plane at a certain distance towards us. And here, this is usually valid if the extent of such a gravitational lens along the line of sight is very small compared to the distance towards us. So usually galaxies have an extent of kiloparsecs, clusters an extent of megaparsecs, and we are talking about cosmic distances of gigaparsecs. So it's more or less a pancake along the line of sight here. And then what we model here are positions on the sky that we see. We do not have the full knowledge where these objects actually are, because in order to do so, we need to have these distances, so we need a cosmological model in addition to actually get the physical distances to these objects here. So on the sky, we can say that the position at which we see the source, y, is equal to the position at which we observe a multiple image minus the light deflection which is caused by the gravitational lens. And this light deflection angle caused by the gravitational lens here, this is usually modeled as the gradient of a dimensionless gravitational potential. So we assume that the gravitational potential causes this light deflection here. And if we want to go to physical quantities here, of course we have to use the cosmic distances here, using a cosmological model in addition. And as you might have already guessed, we also have a standard potential theory to relate the dimensionless two-dimensional gravitational potential in the lens plane here to a mass density, which is now also scaled to be dimensionless, in this two-dimensional lens plane. So we have the Poisson equation here relating the potential to the mass density. And in order to confuse people, we introduce new terms. So we call this scaled mass density convergence. But that's it. So this is more or less the formalism that we have, and what people usually do, because we neither know the source position, nor do we know the full potential, nor do we know the full mass density distribution here. We usually make an assumption of the global mass distribution of such a lens. So we use a model for the potential or for the mass density, and then we can take the gradient of this, insert this as a deflection angle, and then we can solve for the source position because we make an assumption for the mass density distribution, breaking this chicken egg degeneracy that we neither know the lens nor that we know the source. So what we get in the end, based on this lens model, we can get mass distribution parameters for the lens model, and we get position of the sources in this way. But we make an additional assumption about the mass distribution in the lens. What is the impact of this lensing mass distribution on our interpretation of the data? And in order to investigate this, we have to ask, can we do lensing without this lens model? What is the maximum information we can get out of this set of equations without making any assumption of the lens model? So we want to use data, not models, and we want to get back to the formalism and link the formalism directly to the observables without making any assumption about the global mass density distribution in the lens. So let me show you the equations again in a more systematic way. So we start with the conventional potential theory, where we have the arrival times of our light rays emitted from the source at our telescopes being modeled as a so-called Fermat potential, a generalized potential, which encodes one part of the geometrical distance deflections on the way from the source to us, and a deflection caused by the gravitational lens at the position of the lens plane. And setting up this potential has the nice feature that if we now look for the extremum points of this potential, we get our lens equation, meaning the extremum points of this potential determines our multiple image positions. And then we can go on and we can say at the multiple image positions in the vicinity of these points, we can Taylor expand our potential again, so that we get a linearized lens mapping at the positions of these multiple images and in the vicinity. And here we have the linearized lens mapping encoded in what is called the distortion matrix. And as I said, we have multiple images. So one source is mapped to multiple images, meaning we have a non-unique transformation here. And the regions in which we expect these individual multiple images are surrounded by the so-called critical curves. So we know, when we know the critical curves, where the different regions are where we expect these multiple images. And these critical curves are determined by the determinant of this distortion matrix equals to 0. That's the formalism. This is all we have, and we're not allowed to make any further assumptions. And now let's have a look, what are the observables that we now want to insert into this formalism. And here we have a few different cases, depending on how lucky we are in our observations. In galaxy cluster scale lensing, we sometimes have the luxury that we actually see small distorted copies of the source. So we can find individual features in each multiple image that actually belong to the source. For instance, star-forming regions, or some kind of like dust bands, or something that is actually found in all multiple images, so that we can say it looks like all of these features belong to the source. It's the source property. And we just get distorted versions of them in each multiple image. This is what I call the resolved case, because we can resolve individual features in each multiple image. But normally we're not so lucky, and we only find specific configurations of like intensity blocks, like just like surface brightness distribution of galaxies, and then they are arranged in a certain relative configuration. For instance, we have the so-called cusp configuration, consisting of 3 multiple images, 1, 2, 3, and they have more or less a parabolic shape. Or we can find a fold configuration where we have one image and the mirror version of exactly that image, and the critical curve just travels between the two of them. So we have one image and then the mirrored version of it. And for the highly symmetric case of galaxies, we can also observe 2 giant arcs, one really large arc and one really small arc, and this is the 4th configuration that we usually find. So these are the observables that we have. Now, what can we do with these observables here inserted into this formalism? It doesn't sound like much, but actually my colleagues and I, we found that we can determine certain properties that are really valuable and helpful to interpret these configurations. So now let's go back to our resolved case, and let's assume that we can identify at least 3 linearly independent features in image number 1. Then, around one point in image number 1, we can use the linearized lens mapping, and we can have a distortion matrix for this image number 1, which allows us to transform image number 1 back into the source plane and get a source reconstruction. The same thing can be done for image number 2, and we can also set up a distortion matrix to project this one back to the source plane. This is in the formalism. And on the observable image plane here, we can set up, to leading order, a linear transformation that transforms the features in image number 1 to the corresponding features in image number 2. And this linear transformation, which is totally based on observables here, is nothing else than a product of these distortion matrices in the formalism. Because the linear transformation here on this observable plane is nothing else than projecting back image number 1 into the source plane and projecting forward the source plane onto image number 2, using these 2 distortion matrices at these 2 multiple image positions. And if we have at least 3 multiple images with 3 features inside, we can solve uniquely for ratios of convergencies, meaning local differences in mass density, and we can solve for something which is called the reduced shear, which is the distortion of the lens at a particular place divided by the mass density that's sitting there. So it's a measure of distortion per mass density. And these local lens properties can be shown mathematically to be the maximum information that all lens models have to agree upon, because this is the information that comes directly out of the formalism without making any additional assumptions. This is very theoretical, but now let me come to some applications where this one is really worth gold in order to resolve controversies and in order to gain information in the first place. And most of the work that I'm showing here has been done by my undergraduate student from Carnegie Mellon University, Joyce Lin. She did a really great job in analyzing all these cases. So let's have a look at the first case. This is called Hamilton's object, named after Tim Hamilton, who discovered it. And we have a freshly discovered galaxy cluster at this redshift here. We have 60-member galaxies, and we have a cluster center based on the red mapper software, which is based on some red sequence galaxies. And we have this beautiful textbook example of 3 multiple images here in this region of the cluster, and we have spectroscopic confirmation of all of these redshifts. So we know that these 3 multiple images belong to a configuration. We have 3 multiple images, so they could be a cusp configuration, as we learned beforehand. But that's it. We do not have more information here. So this means we cannot fit a lens model or any idea of a global mass density distribution to 3 data points. This doesn't work. But using our local approach, we can infer quite a lot. So let's have a look at the local shear per mass density. We have certain directions of these shears, and so we can see here, if we plot these directions, that this cusp configuration hints at the cusp at this point here, so we can conclude that the light deflecting mass must be located somewhere around here, because this is what usually happens in these cusp configurations. But RedMapper identified the cluster center somewhere up north here. So we can learn here, either RedMapper misclassified the center, or we have a merger out of several clumps. This might be possible, and this is a hypothesis we can test with further data. And this is all done by just identifying these 7 features in all of these multiple images and mapping them onto each other. Just like I showed you in the previous slide for the theory, how we can set up these local lens properties based on the features that we measured. And another point that we can check, I told you that we can solve for relative mass densities. We find that this is just as we expected, that the highest density is found at the innermost image, and when we go outwards, we have lower mass densities relative to the one in the center. So everything is like as we expected. And now comes the best part. Maybe you've heard about dark matter properties, and that we should see what the smoothness scale of this dark matter could be. And here, we do not need any model assumption, but we can put a constraint on the smoothness scale of dark matter. If we take a look at these 2 multiple images here, which form a fold configuration, because we have here image number A, and image B is a mirrored version of image A. So now, let's have a look at this fold configuration, and we have 7 features, which are multiple images on their own. So now let's take a look at feature number 7, and we have feature number 7 in image A and image B. So we can use a linear Taylor approximation in order to get the point on the critical curve that is between these 2 multiple images. And we find this as just like the point here, putting the distance between these 2 multiple images into halves. And we can do this for all other features as well. And we find that actually all of these points lie on a line with very tight confidence bounds. And this means that we have a linear approximation to the critical curve here in this vicinity. This means that the dark matter has to be smooth there. If we had some clumps, like black holes or so in between, then we wouldn't see a line, but we would see some disruptive events here, which would not end up in a line. So between these multiple images here, we have like about 1 arcsecond, and this corresponds, using a cosmological model, to physical distances of about 6 kiloparsecs. So we know here, locally, that the dark matter must be smooth on a scale of about 6 kiloparsecs based on our data evaluation. This is, I think, quite impressive given that we couldn't do anything with lens models. So far so good if we have sparse data. Now let's come to another example, which is one of the most exotic lenses I've ever seen. And this is a thing which has been modeled to death because people saw this really nice, huge cusp configuration and these two multiple images on the other side. And they said, come on, this is a really great case where we have a multitude of data, so we can now set up a lens model. And this lens model then gives us an idea of the total distribution of mass in this region here. And then we compare the total distribution of mass, including the dark matter, with the luminous distribution of mass that we see based on the galaxy distribution. And this one is an exotic case because we see 4 equally bright central galaxies and even a 5th one here. And this is not what we expect normally, because normally we have one bright galaxy in the center and everything is just like monotonically decreasing upwards. So people said, now in this example here we can learn something, whether light traces mass or not. So is the dark matter distribution offset to the luminous matter distribution or not? And the first models were really crude on very crude data, and they found a huge offset. And then people said, what properties does dark matter have to have in order to have this huge offset between the mass and the light? And particle physicists said, sorry, but we do not have any candidate for dark matter that would fulfill this property. So people went back and did some better modeling, and in particular gained a lot of additional observations to resolve the case. And with increased data quality and with increased model quality, this offset became less and less prominent. And in the end, people said, we do not think anymore that light does not trace matter here. So actually, it seems that everything is normal as expected. But this was based on assumptions in the image processing, because in order to get all these little features here in these multiple images, some people said we need to subtract the foreground light. This is based on certain assumptions about the light distribution here. And having models in this highly, anomalous case, how do we model this distribution of galaxies? How do we model this smallest galaxy cluster center if this is really dynamically very active, definitely not virialized? What do we know about this in order to set up such a model? So this is all like the unknown stuff, which may impact our data interpretation. And another point that we found was quite interesting is that normally galaxy clusters are at very far away distances, so a megaparsec extension doesn't make anything. But here we are talking about a galaxy cluster in our backyard. It has a redshift of about 0.09. This means we have a distance of about 400 megaparsec to this gravitational lens. The source is at like 1.5 gigaparsecs. But this extent here that we are given by the redshifts of these 4 galaxies here hints at the fact that the extent of this galaxy cluster along the line of sight is about 10 megaparsecs. And this extent compared to the distance to us is 1 order of magnitude larger than we usually have if the galaxy cluster is farther away. And so here we ask the question as well, do we see 3D effects in this gravitational lensing effect? For instance, I would say smoking gun for 3D effects is if we have relative rotations between multiple images, because normally we can only distort and scale upwards or downwards, magnify or demagnify, but we cannot cause rotations. And if we see rotations here, this is also a clear smoking gun for potential 3D effects that play a role due to this very proximity of light. So now let's have a look systematically what impact do we have. This has not been possible with lens models because we always have the lens model impact as well, which is hard to disentangle between what's the model assumption, what's the data, because fitting the data usually gives you just the parameters of the model. So first and foremost, we thought when we identify the features that should be matched across all multiple images, we might be able to identify features that are just transient events that are just like going on and going off again, and which may bias our interpretation. But luckily, we had data from about 10 years of data taking, and all the features that we saw were more or less stable. So every brightness plot that we identified was actually stable across this time scale. And we also had like multiple observables from news data, from HST, from AMA, and all of them jointly hinted at a very robust feature identification here. Next point is, which features do we find given that we have a really low signal to noise event here? So we used the most prominent filter band in order to identify the background features where the foreground light was hardly visible, and we could actually do the identification without any foreground light subtraction. This was our credo, that we didn't want to make any assumption about the foreground light. And here, what we found were 6 features that we could identify across all multiple images. And our other teams, they just used multiple bands and they subtracted the foreground light. And what we can see here very prominently, that we do not find a significant detection in this region here, while the other people using multiband detection all have a feature here, which is called feature 4 or feature C here. But if we take a closer look at the color profile of this feature, particularly here, it looks very similar to these points here, and these points were clearly foreground noise coming from some globular clusters in the foreground. And so what if the feature that is identified here is actually a foreground point and not a feature of the source property? How does this impact our interpretation of the data? The second point that we raised is we can match these features in different ways, because a brightness plot is a brightness plot, and if we have very small and ambiguous image shapes, which feature in which image belongs to which feature in which other image? Highly difficult task, non-trivial. And what we found here is that there are 2 possible ways to see this little configuration here, which is close to galaxy G1. Our image processing algorithm, which is based on quantitative features, noise reduction and all this, we found that we have a fold configuration here, meaning one image in this direction and then the mirrored image in the other direction here, based on the features that we identified. The other groups here, they found a configuration which has a parity in this direction for the first image and exactly the same parity in the other image. This is not what we expect from a fold configuration, but it requires additional explanation. How can we have a critical curve between these two and the same parity for these 2 multiple images? This can be explained if we have at least 2 mass clumps forming this gravitational lens. So it's not, it's not impossible, but it's still a bit unusual. Nevertheless, this configuration may allow for this. So we now have 2 different, or at least 2 different interpretations. How can we interpret this configuration? So these ambiguities have to be resolved, but it's really hard to do so because we cannot argue for one case or for the other. And I hope that people from weak lensing can actually break this degeneracy, because there are some hints that we have, for instance, when we do a lens model for this stuff here, that we see certain mass distributions in the outskirts of this galaxy cluster. And if weak lensing actually coincides with this, then we have a clear hint that this is actually the right configuration. And if we do not find any optical counterparts and weak lensing signals where the mass is predicted, then why not assume that we have this configuration and that we actually have a 3-dimensional thick lens? It's possible, and we have an hypothesis that we can actually test with further data. But now, let's see what is the impact of all of these different varieties on the local lens properties. And here, I think it's pretty nice to see this for the first time, that we can directly show what is the impact of this feature identification and feature mapping on the local lens properties without using any assumption about models. And here we clearly see for this cusp configuration here, our identification is the red arrows, and the arrow indicates the amplitude of the reduced shear, and the direction is along this entire line of the arrows. So we see that we differ in amplitudes and that we differ in directions for the local shear here in this configuration. And we also see here, they're just like red arrows here. And this is because the other approaches that we used here were so close to the critical curves that the arrows exploded and we couldn't make a clear prediction for the directions and the amplitudes at these 2 points here. So what we see here is the clear impact of the feature matching. It differs, and we know how it differs for the first time, that we now know how does the data-based evidence translate into local length properties without using any model. And what we also find pretty interesting, and so far I just used all 6 features of the entire image region here. But our algorithm is equally valid to chop this huge image up into little pieces and then see, do we find stable local length properties for all of these individual combinations of features? And the answer is no. So this means that the gravitational potential and the mass density vary even on the scale of these multiple images. So it's not constant, it's not smooth. And this in turn means that we cannot even say anything about the mass density distribution at this galaxy G1 because the mass density is changing so quickly that we even have to chop up the multiple images into individual small regions to make stable length features. Yes?
I have a question.
Yes?
If I understand correctly, so in your approach, basically you assume that basically because you use the linear mapping approach, so the convergence and shear is assumed to be constant in
Yes.
each square region.
Yes.
So it means that neglecting the next higher order term, basically flexion,
Yes.
curvature,
Yes.
and central shear.
Yes.
Does this affect your interpretation in this context? With mass distribution not kind of potential vary in this region.
Yes, yes. I mean, actually, that we use the breakdown of the linear approximation.
Okay, already.
We actually exploit this fact that it's not constant anymore to say here this breaks down, and this means that the potential has higher orders that we need to take into account. And I think if we now want to take these higher orders into account, we face different degeneracies again. And so the question is, in how far does the lens model give us a good prediction for this region here if we are already suffering from a linear approximation here? I mean, the lens model assumption then totally drives everything that is said about this position here because it's so far away from the data and the potential is changing so quickly. And so I would say this is exactly the reason why we have a hard time to say light traces mass or light doesn't trace mass in this case here. And I think the approach that we did by showing that the linear approximation breaks down actually shows that we cannot say anything about light traces mass at the positions of the galaxies because we can prove that model assumptions totally drive our conclusions here. That's exactly the point. And it was highly non-trivial to get to this result. So let me summarize the first part now. What have we learned without making any model assumptions? We have a local description for strong gravitational lenses, and we have data-based quantities, which are just, at small portions in the lensing region. But we can easily compare all of these local length properties because they are just like numbers that we can compare between different galaxy clusters, different galaxies, and so it's as easy as comparing lens model parameters. And the most important point for me is that we have a clear understanding where all the degeneracies come from, be it in the formalism, be it in the lens model, and we know where and how to get additional data to break these degeneracies. And this is possible because we separate the data-based evidence from the additional model assumptions in this approach, and this makes it very efficient to be used to explore very sparse data sets, and on the other hand, to also get a reconstruction which is highly efficient if we have a high coverage of multiple images. James Webb was a bit of a disappointment here. We expected 1,000 multiple images per galaxy cluster. We didn't get this, but imagine we get 1,000 multiple images per galaxy cluster. Then this approach here, this patchwork approach, just uses all the individual multiple images, gets the local lens information in such a region, And then, due to the high coverage, we can just interpolate between individual information to get the least model-dependent mass density map of galaxy clusters or galaxies or even larger structures. So this is highly efficient and it's 100% understandable physics. But, I mean, this is just explanatory. We do not get any model here in this approach in order to make a prediction, to go out and test our prediction and then to corroborate our model. This is what we usually want to do in astrophysics. And so, if we want to have models in the game, then I think we should at least use models that are based on sound theoretical fundaments, so to understand how far should the model lead us and where does it break down. And this is why sometimes we need lens models in order to make predictions where are more multiple images or what is the distribution of such a galaxy or a galaxy cluster in order to corroborate these models to actually believe that these models are a good description for our object. And if we now take a look on galaxy or on galaxy cluster scale lensing events, it's super hard to distinguish which one is which. We have a kind of universal conspiracy here that it seems that nature prefers power law densities from galaxy to galaxy cluster scale. And people set out to do simulations, and maybe you've heard about the famous Navarro, Frank, and White mass density profile. Here we have a heuristic function to describe a three-dimensional mass density and how this scales in the central part with 1 over r, and in the intermediate part with 1 over r squared, and in the outskirts with 1 over r cubed. This has been found by simulations, but nobody understood why. Why is this model looking like this? Why isn't it just a simple isothermal sphere where we have 1 over r squared for the entire dark matter halo? And so I set out to say, can we base our heuristic fitting functions here, I mean we have a whole zoo of them, can we base them on fundamental physical principles? Can we explain why they have to look like this? And in order to do so, we first have to see what do simulations find. So let's have a look at cosmic structures in simulations. If we take such a dark matter halo, then we find that in the outskirts we have power law exponents of like 4 to 3. And if we go to a little bit inner parts, we find the so-called isothermal slope, like power law indices of about 2. And then, depending on which simulation we use, we find various power law indices in the central part. So here, the simulations do not agree whether we have a power law index of about 1 for the MFW profile, or some other shapes that we find here. So from 0 to 2, everything seems to be possible. So if we want to understand dark matter structures, or in general gravitationally dominated structures, we have to explain what happens here in the central part, and we have to reproduce the more or less agreed upon power law indices in the outskirts. In order to do so, we first have to set up all the prerequisites that also go into these simulations, because we want to explain these power law indices. And so we have the microscopic ensemble of particles in these simulations. They are usually a bunch of identical and identically distributed point particles, and they are assumed to be collisionless, which translates into independent particles. And mostly, they are based on Newtonian gravity as the only interaction. So I'm not talking about dark matter, but I'm also talking about any structure based on gravity as the dominating force. So it can also be baryons as long as gravity is the dominating part of it. And this has the neat feature that all the pairwise gravitational interactions can just be summed up in order to get an effective total interaction. But this is the macroscopic picture. What we want is a continuous mass density profile, meaning we have to coarse grain this into a macroscopic picture. And the macroscopic picture is that we have a halo, like a finite structure, a structure of a finite radius. And here we usually assume that it's spherical, but we could also change this geometry. And what we also want to have is that we want to have that this halo has a scale-free spatial power law probability distribution. And this is an ansatz that I'm making which I still have to kind of like reason a bit deeper. But because Newtonian gravity is a scale-free interaction, and it has this 1 over r squared pairwise interaction potential, let's make the approach that the probability for one individual particle to be at a certain point follows some power law profile. This makes sense, I think. And so if we do this, we still have to normalize this probability density function. And this normalization constant, of course, is an integral over the entire volume of the halo times the probability. And this means that the probability of finding a particle that belongs to the halo in this halo is actually 100%. And so this normalization here encodes the geometry of the halo, and it also makes a statement, it's also dependent on this power law index. So this is just the probability density function for one individual particle. Now let's take an entire microscopic ensemble of particles, which consists of this NP collisionless independent particles. So if we want to have a joint probability density function of NP particles being at certain positions, we just multiply the individual PDFs to get the total probability density function for an entire ensemble of particles. And then we can always take the logarithm of this, mathematically no problem. And now comes the interesting point. We're interested in the behavior of the power law index, and so I'm asking, what are the extremum configurations of these particle distributions with respect to the power law index? So I set up this extremum configuration problem, and so by inserting all the prerequisites for the PDFs here, I end up with this ugly equation. But this ugly equation has a physical meaning. It means that here the first term is a function of the normalization constant, meaning this encodes our macroscopic halo model because it encodes here the geometry and the dependence on the power law index, and it is now connected to the individual particle distribution in the second term. And here you see that this depends on the number of particles with which we sample this mass density, and it also depends on the individual positions of these objects. This is just a mathematical neat equation. Now what does this have to do with our mass density profile? We're just talking about probabilities here. Well, the mass density at a certain position is the mass of one particle, we assume they are identical, times the number density of particles at this position. The number density of particles is the number of particles times the probability of one individual particle to be at this position, due to all the prerequisites that we made in these simulations. And so, inserting our individual particle distribution density function here, we find that the power law index that we get out of this equation is actually directly the power law index of the mass density that we want to describe. So let's have a look at the specifics. If we insert our spherical halo and our finite max, then we find that this power law index, based on the previous extremum equation, is 3. This comes out of 3 dimensions for the mass density, plus, and now this term here encodes the number of particles that are used to describe the continuous mass density. And here, this is super important, the individual positions of all the particles with respect to the maximum extent that I give this halo. So the scaling radius that I had, this r sigma in all of the equations, just drops out. It's an auxiliary thing that has no physical meaning. The physical meaning here in this power law index is the number of particles, the positions, and the boundary that I set for this halo. So now let's jump immediately into the center of a dark matter halo and ask, what power law index do I find there? Because all the simulations, they didn't agree to a specific index. So what is there? Well, it's the region where particles fly through with the highest velocity. And it's the region that is sparsely sampled in simulations. We hardly have any particles there. So the power law index here definitely depends on the number of particles, And it definitely depends on the specific positions of all of these particles with respect to the boundary of this central part. And so the power law index here is not, it's not a single power law index. It depends on the specific halo that I look at. And this is actually the explanation why these simulations do not agree on a specific power law index in the central part. If you take a look at this one and the limiting cases, anything from 0 to 2 is possible. And if we take a specific distribution, radial distribution of particles being uniform, we happen to recover gamma equals to 1, which is the index of the Navarro-Feynman-White profile. Next part. Let's go a little bit outside of this central part, and let's increase our boundary. Then we encounter a lot more particles, a whole lot more particles. So what if, in the limit, we let the number of particles go to infinity? What happens to gamma then? Well, then gamma will be equal to 2, which is the isothermal fluid case. And this, in physical terms, means that we have so many particles to perfectly represent our perfect fluid. And this is why we get the isothermal fluid case here as an intermediate regime. Then, for the outskirts, we have two possibilities. We can either say we are looking at galaxy clusters, which are, I would say, usually modeled as isolated objects in the huge universe. So let's assume that gravity reaches out to infinity. But our simulations, the halos there, are cut at a finite radius, which are, and this radius is much smaller than infinity. So meaning our particle distribution here is at radii much smaller than our max. And in the case that we let our max go to infinity, we recover gamma equals to 3, which is actually the outskirts of an NFW profile. And this means here that our particle distribution in our simulation falls short of the boundary that it actually has. The opposite case is recovered for galaxies. Galaxies are usually in a background environment, and they are alone, and we have a hard time to distinguish the galaxy from the surroundings. So where does the galaxy end? We usually use what we call half light radii, and if we do exactly the same and we define a half mass radius, then cutting our structure will certainly not end with the particle distribution that is attracted by this halo. So the particle distribution here spills over our max, and in this case, if we do this approximation here, we find that gamma equals to 4, which is actually found observationally and in simulations for galaxy scale Wagner halos. So all in all, we are able to describe all different power law indices based on these equations, on these simple equations. And from the physical point of view, this is, as George Ellis called, trivially true, because if we take a look at scale-free gravity and we have a potential that is a power law, and we assume that we have Newtonian gravity, so we can use the Poisson equation, then any mass density coming out of this Poisson equation has to have a power law as well. And James Binney already said, if we have self-gravitating particle systems, then we can neglect their kinetic energy to leading order. And this is what I did here as well. And this is true because these particles will spend most of their time and are most likely to be found at a position where the kinetic energy is 0 and the potential energy is at a maximum. That's where they spend most of the time, so this is the most likely place where we will find them. That's exactly my approach as well. And so this is supported here by this paper by Binney from already 1982. And last but not least, the collisionless nature of the particles that we assumed actually means that we represent a perfect fluid, which then again calls for self-similarity. So all the power law indices are more or less coming from the fact that we are sampling a perfect fluid with imperfect distributions of samples. And so we have a minimum radius. Below this there might be demons, we don't know. So we have at least a minimum radius. And then we start to collect particles in the simulations, and we find these different power laws depending on the sparsity of the sampling and depending on how we cut out our structure from the environment. And remember, gravity is scale free. I didn't include any other forces than gravity. So how we chop up the structure into our structure and the rest of the universe is more or less emergent. It's arbitrary because gravity doesn't give us a certain scale at which we should cut the object. For this, we need some equilibrium states and we need to include velocities in order to find a preferred scale, how to distinguish a structure from its environment. This is why I called my theory DEMON, for dark emergent meta-halo explanation. And so let me now conclude in total and let me summarize what have we gained from including these models. So from the first part, we know that we have local information and we can separate the evidence and the model assumptions, but we have degeneracies that are still that we still need to look at. But if we have very sparse data, we still have to beef this up with additional models. If we want to beef this up with models, they should be based on fundamental physical principles. And here, I would say that we can now reason that power law mass density profiles have a deep fundamental reason to be there based on these self-similar, self-gravitating scales. And so we have here a global information if we insert this model. And what we also find is that the shape of these power laws is then really supported by these fundamental assumptions. And the gravity-dominating structures, they are self-similar. So anything that deviates from this power law profile must have some baryonic additional interaction, or must be an open system that can exchange particles with the environment or something like this. So we know that this approach here will break down if we include additional assumptions beyond just simple gravity. So all in all, we now understand strong gravitational lenses in the least model dependent way, and we have a reason why we should use power laws if we want to have a model. So for the rest, happy afternoon, talk is over. It's not happy Christmas, as Don Lennon's saying. But thanks a lot for the invitation. And if you have further questions, even a week later or so, here's my email address and here's my homepage. And if you want to talk about this idea, how to derive power law densities, there are also two works here that I published so far, and I would be happy to get some further inspirations for this, because this approach is still in its infancy, as you can see, and it needs to be extended.
Very nice talk. I have two questions.
Yes.
The first one is about the last part of your talk, about this density profiles for the self-gravitating system. Yeah. So it reminds me of the work, theoretical work done by Jens and Lillian Williams. So they developed theoretical model that describe the density profile for the self-gravitating collisionless system. Assuming that dark exponential model.
Yes.
Assuming that they are isolated, it means that there's no surface time, and they do the symmetry argument, energy distribution particles. So the resulting profile depends on the central depth of potential. But basically they reproduce inevitably right, but actually the Hank is right because they are isolated system. Yeah. So
and it was just an approximation as far as I understood. I mean, it was not perfectly fitting.
Okay. Yeah. Yeah.
Yes.
So in this context, I want to know what is actually a boundary condition you assume. It seems like your model describes some local distribution of the particle. Yeah.
Yes. Yes. I mean, the fundamental difference between their approach and my approach is that I played a kind of taboo game, because I think that the fundamentals that they are relying on is conventional statistical mechanics, meaning they have an ergodic sample and they are using exponentials, like, I mean, this standard chi-square distribution and the phase space and all of this. And I think we are not allowed to use this at all. This can only give us an approximation to quasi-stable states. But gravity is not ergodic. Gravity is not, I mean, it doesn't cover the entire phase space if you let these particles propagate long enough. It's exactly the opposite. Gravity is just like collapsing everything. And this is why you have to find a way to avoid this entire formalism to describe your structures, because otherwise you will never find a fully, I would say, more general theory. So for quasi-stable states, the statistical mechanics, the virial equilibrium or quasi-stable equilibrium is totally fine, and this is why they only get an approximation, because they're still relying on this. And this one is completely the opposite. It does not make any assumption about this, and this is why I just talked about probability density functions and not about canonical examples, microcanonical examples, and all of this. And the isolated system, actually, yes, this is definitely this case here. And so where we truncate our structures, in this formalism, it's arbitrary. So it depends on what physical assumptions do we make. As I said, let's put gravity's interaction to infinity. Then the maximum radius would be at infinity because everything is attracted to this halo. Then you have one single isolated structure dominating the entire universe. But if you embed this in a background, then of course you have to truncate it. And where you truncate it is, I would say, in this case, still arbitrary for you, unless you say you have additional velocities and you have some conservation laws that you can include to get a preferred scale. But gravity doesn't give it to you. And if you go to general relativity, you're facing exactly the same problem because it's also scale-free. So you need some additional conservation laws to get a preferred scale.
I see. So in your model, so do you also incorporate this like a velocity anisotropy of particles or something? That kind of degenerate with kind of impacts through like a Jeans equation.
Yes. That's a good point. I mean, I haven't talked about the velocity information so far, because if you have energy conservation, then the information you get from the positions is exactly the same as you get from the velocities. So you can translate one into the other. But if you violate this and you open up your system, then of course you have to solve the Jeans equation and you have to take a look at the velocity distributions, giving you complementary information.
Yeah, that's again the equilibrium assumption. Kind of.
Yes.
My second question
is
about the first part. Yeah, so let me how to form it. Yeah, so from it's not very clear to me how this massive degeneracy is encoded in your kind of results. Because you are using the relative information of the magnification and deformation. So the combination constraints should suffer from that constraint.
Super question. Nope, it doesn't. And the point is, I mean, the mass sheet degeneracy is more or less, So, yes, we have a mass sheet degeneracy, which is usually assumed, but this means you have a global information, and the mass sheet is more or less stretching everything in the source plane and in the lens plane. And this degeneracy is usually broken by models. And what we do is we try to avoid this discussion altogether, because the mass sheet degeneracy can also be broken by having the distances, the cosmological distances to the mass and the source. And what we assume here is that we have the linear transformations here, and they are not subject to the mass sheet degeneracy as a global degeneracy. So there is no mass sheet, but it's a local degeneracy, and this degeneracy affects the point that we cannot constrain the source morphology up to an overall scale, and we are free to have a global transformation, a global lensing transformation to all images alike. So meaning we cannot constrain small scale lens properties and the source. So this is the degeneracy that we have, which is a local version of the mass sheet degeneracy, which this approach is still subject to, and this can never be broken in principle. So what we do is we make an assumption that we have unresolved sources here, and that every ellipticity that we see at the little small blobs is caused by a distortion of the local lens distribution. So on that scale, we break it by saying, okay, we have just unresolved sources, but in principle, this degeneracy will always be there. And I have a paper I have a paper series, and number 7 constrains deals with this degeneracy and tells it's not being able to be broken in general.
I see. Okay, thank you.
Yeah.
You have to plot up one of the questions that Keiichi mentioned is how good is the assumption that A is a constant across these blobs? But there's another effect, and you already mentioned that if the lens is extended in the 3rd dimension, I think in your model you're still working on symmetric amplification matrices, or that you're not assuming that?
Yes, I mean it depends. I mean for the fold configuration here, we are definitely assuming that we have a symmetry, that more or less the magnification in this image is more or less the same as that one. This for the smoothness scale we need that, but for the rest we are not looking at specific symmetries because we just Taylor expand around each point in the multiple image position, so we can have arbitrary distortion matrices.
Well, arbitrary meaning normally an amplification matrix has 1 plus kappa, 1 minus kappa, and the gamma, gammas, whatever they call it, two gammas and 1 kappa. That's 3 numbers on a 2 by 2 matrix.
Yes.
But if you have multiple planes, then you multiply these matrices, and then you have 1 more degree of freedom. So, so then these, in principle, you could have 1 more. So just in your modeling, you are
this is not included yet.
It's not included.
It's not
it's still a single plane. It's still a single plane model.
Yes, exactly. But it's easy to extend, and I think, if I get further funding, I'm happy to do this because, some people said I'm wasting my time on these kind of like tiny pretty details, but I'm thinking if we take a look at the parities and at the relative positions of these multiple images and the features that we identify, that there actually is a rotation that we see in this cusp configuration. And I think that we should model this as a 3D lens and see whether this makes more sense. Because if we have freeform models, the freeform models are arbitrary to use any kind of like mass distribution. And what we see in the reconstruction outskirts here, we see that the freeform models play around with the mass densities, and they seem to put a lot of mass in this region here in order to get the 2 equal parity configurations here at this point. And so I was wondering if we now take my configuration here, then these masses here are gone. And so it seems that if we have a rotation, that this kind of like lens models try to mimic this rotation as a sequence of shearing and a little bit of scaling, because any rotation can be decomposed into shearings and scalings. And so I think that if we take a look at this case, we may be even able to learn a lot about lens models itself. Like if we have a 3D lens, then we will see certain structures at the reconstruction ends of these freeform models hinting at their own breakdown. And I think this is pretty great.
Yeah, it's a very unique system. Usually we consider multiple plane lensing for like distinct lens planes, but this is a really smooth single system in 3D.
And the individual lens planes, you can only use that if you have spectroscopic information and you know where they are. Otherwise, happy degeneracies, if you're thinking there is something and then you try to model it, there are so many options. So you actually need some optical counterparts to say, okay, here we have an idea why we use multiple lens planes.
Good. So there's tea and cookies out there, so let's continue discussions outside of the tea and coffee. Let's thank Danny again.